Let me welcome you to this lecture. We have been discussing about the chemistry of the hydrides of boron, and so far we have looked at the structure and bonding of these compounds, as well as we have also looked at some of the methods. That is, we have looked at the Stike's number as well as Wade's rule, which allows us to predict the structure of these molecules. Now we will discuss about the reactivity of these boranes. So when we talk about the reactivity of boranes, the borane which is most studied and which is one of the a very important synthetic reagent is the diborane molecule, that is B2A6. In fact, diborane uh, was used as a reagent in hydroboration reaction, and this hydroboration reaction, which was discovered by A.C. Brown and Subba Rao, who's from India, uh, was awarded the Nobel Prize in Chemistry in 1979. So A.C. Brown was awarded the Nobel Prize in Chemistry for discovery of this hydroboration reaction, and we will discuss about the hydroboration reaction also during this lecture. Now before that, let us see how one can prepare diborane as well as the other borane molecules. So in the laboratory, preparation method for diborane is pretty simple. That is, one starts with NaBH4, and when it is reacted with iodine, I2, in diglyme, which is a polyether. So the structure of diglyme is, it's a polyether, and it is used as a solvent here in this reaction. That is the structure of diglyme. And when this reaction is carried out, there is a reaction of NaBH4 with I2. Essentially, NaBH4 reduces I2, and in the process, B2A6 is formed. So B2A6, and sodium iodide is formed because iodine is reduced to iodide, and also there is evolution of H2. So if we balance this reaction, then we will have 2 Ni over here, and the reaction is essentially balanced. If we put 2 NaBH4 plus I2, it essentially gives B2A6 and sodium iodide, and 1 mole of H2 is also released in this reaction. Another very popular method or laboratory method for preparation of B2A6 is one starts with NaBH4 again and adds an anhydrous acid like H3PO4 here, phosphoric acid, and again what we have is here B2A6 is formed, which is gaseous in nature at room temperature, and then we have NaH2PO4, sodium dihydrogen phosphate is formed here, as well as H2 is formed here. So if we balance this reaction here, so we'll have B2H6, so we'll have to put 2 also over here, and this is also going to be 2. And then we balance the number of hydrogen, so 8 plus 6, 14 hydrogens, 6 plus 4, 10. So 2 moles of hydrogen are released in this reaction when we obtain B2H6. When we react NaBH4 with anhydrous acid like phosphoric acid, one can also use anhydrous acid like H2SO4, and it essentially results the diborane molecule as a gas, and this can subsequently be used in for different synthetic as a synthetic reagent in different reactions. So that is how one can prepare the diborane molecule, and the other boranes, that is higher boranes, can all be prepared starting from the diborane molecule. So what one does here is that other boranes or higher boranes can be prepared starting from a diborane by the pyrolysis of diborane in sealed tube at higher temperature. So the mechanism of this reaction is known only very recently, that is during the pyrolysis of diborane in sealed tube. Essentially what happens is that, so pyrolysis of diborane. So this results other higher boranes, and the mechanism of this reaction, in the first step, diborane undergoes unimolecular dissociation into BH3. So now BH3 is a transient intermediate, so it is not stable enough to be isolated, and that is why we put it in this such species which are only transient or which exist only transiently. We put this curly bracket to denote that such species are only transient intermediates and cannot be isolated as such. So now once BH3 is formed after dissociation, that is after unimolecular dissociation, and this reaction is in equilibrium because BH3 itself will undergo dimerization to result B2H6. Now once BH3 is formed during a pyrolysis, it can react with B2H6. So BH3 is going to react with B2H6 to result another transient intermediate, that is B3H7 plus 1 mole of H2 is also released during this reaction, and now this B3H7 will react with BH3 to give the first stable intermediate during the pyrolysis of diborane, that is both of these two transient intermediates, that is BH3 and B3H7, can react to give us B4H10, which is the first stable intermediate formed during the pyrolysis of diborane. And then further reactions can occur, that is this B3H7 can react with B2H6 as well to give us BH3 once again and B4H10. The same reaction can also result B5H11 plus a mole of 1 molecule of dihydrogen. So this is under a stable intermediate that can be formed during the pyrolysis of diborane, and in fact all other higher boranes can be prepared during the pyrolysis of diborane. That is, one needs to optimize, or one needs to the reaction temperature, pressure, and time to isolate specific boranes in good yield. So one needs to, during this pyrolysis reaction, one can optimize the temperature of the reaction as well as pressure of the reaction and the reaction time, and this will allow one to isolate different borane in good yields during this by doing this pyrolysis of diborane. So one example of optimized reaction condition to isolate a specific borane molecule in good yield during the pyrolysis of diborane is that, so when we take diborane and leave it at 25 degrees Celsius under high pressure condition for 10 days, so one obtains B4H10 as the major product during this reaction. So that is how one can prepare B4H10 starting from B2H6, and just leave the B2H6 or diborane sample in a sealed tube at 25 degrees Celsius under high pressure for 10 days, and one will have B4H10. So similarly, other higher boranes can be prepared in good yield by optimizing the temperature, pressure, and the duration of the reaction, and that allows preparation of most of these borane molecules. Now what we have seen over here is that BH3 itself, BH3 is a transient species. Which cannot be isolated as such, but one can use different matrices to isolate BH3. Of course, it can be isolated only in small concentrations. And the another way to trap BH3 is to form 1:1 Lewis acid base adduct with other Lewis bases. So this, because this is a Lewis acid, because it is electron deficient, we know that already. So it is going to form 1:1 adduct with Lewis bases. So examples of Lewis bases, we know Lewis bases like ammonia, or say for example carbon monoxide is also a Lewis base, phosphines are Lewis bases. So these sort of molecules which are Lewis bases are going to form 1:1 adduct with BH3, and these adducts are quite stable at times, and that is how one can trap BH3 molecule. Now one of the very important reaction that involves formation of such adducts is when one starts with the diborane molecule, that is because BH3, the source of BH3 is diborane. So when one starts with diborane and then reacts it with different Lewis bases, one obtains the Lewis acid base 1:1 adducts of BH3 with different Lewis bases. But during this reaction, the cleavage of diborane molecule into BH3 can occur in two different ways. That is, this is diborane, and it can undergo homolytic cleavage. That is a Lewis base, say, L. It can undergo homolytic cleavage into two BH3 units, and that will essentially give us 1:1 Lewis acid, a base adducts of BH3 with different Lewis bases in this way. So this is homolytic cleavage of diborane. And this happens when the Lewis base that we use is sterically bulky in nature. So sterically bulky Lewis base when we use, then we trigger the homolytic cleavage of diborane molecule to give us this sort of 1:1 Lewis acid base adduct of BH3. Then when we use sterically less bulky Lewis bases, one may trigger the heterolytic cleavage of the diborane, that is, it may undergo dissociation or cleavage in this way, so that we have heterolytic cleavage. So what we will end up with when we have this sort of heterolytic cleavage, so this sort of Lewis acid base adduct of diborane, that is, and another adduct that is also Lewis acid base adduct only, because this is an adduct of H negative with BH3. So what we have is the BH4 anion is essentially formed during this heterolytic cleavage of diborane, and we can consider this anionic species as a Lewis base adduct only again. Like when we consider that this additional hydrogen atom that is attached to the boron is essentially a hydride ion. So this sort of 1:1 adduct of Lewis bases can be formed with the diborane molecule. Now diborane undergoes different types of reaction apart from such cleavage reaction, or which leads to formation of adducts with Lewis bases. So other kinds of reactions that diborane undergoes are substitution reaction. So one can substitute some of these hydrogen atoms by other groups in these type of reactions. Then there is also a reaction where redistribution reactions can also happen here. And apart from that, another important type of reaction is solvolytic reaction, like the hydrolysis of the borane molecules. So during hydrolysis of borane molecules, one essentially obtains H3BO3 or boric acid as the product in all the cases. But when one uses alcohols or during solvolysis reaction involving alcohol, or what we can term these reactions as alcoholysis reactions. So one example of such alcoholysis reaction is when we treat diborane with methanol. So alcoholysis reaction is going to occur here, and we will end up with BOCH3 three times, which is a volatile liquid and can be distilled off the reaction. And we will also have 6 moles of hydrogen during this reaction. So because this is 2, this is also going to be 2, and this we have to write as 6 here, and we will have 6 moles of hydrogen coming out during this reaction. In fact, at one point of time, people used to estimate the number of hydrogen atom in borane molecules by such alcoholysis reaction or methanolysis reaction, because during this reaction the number of hydrogen molecules that are evolved is essentially equal to the number of hydrogens present in the borane molecule. But this procedure could be used only for nidoboranes and arachnoboranes, borane molecule. So only in, let us write as nido and arachnoboranes. because closure boranes are too stable to undergo such alcoholysis reaction, while only nido and additional boranes undergo such alcoholysis reaction, and we can find out the number of hydrogen molecules in such nido and additional boranes by doing this methanolysis reaction. So we already spoke about one very important type of reaction where diborane is used as a reagent, that is the hydroboration reaction. And you may have already learned about the hydroboration reaction in organic chemistry, where we know that this hydroboration reaction undergoes in a anti-Markovnikov fashion, that is, the hydroxyl group is essentially introduced to the less substituted carbon atom in an olefin. So in hydroboration reaction, we know the diborane essentially reacts with undergoes 1,2 addition with olefins or with even alkynes. So B2H6. So what we will have is, let's put half over here, because then what we will have is the hydrogen atom of the BH3 group will essentially be added to the more substituted carbon atom over here, and the less substituted carbon atom here, or the terminal carbon atom of the olefin over here, will be attached to the boron center, and we will have this sort of an intermediate forming. But once we add another mole of this olefin, or another 2 moles of the olefin, these 2 hydrogen atoms of this borane will essentially be replaced by the olefin over here, or the olefin. This will undergo again 1,2 addition reaction with the olefin here to give us this is CH2 B 3 times. This sort of a product is essentially obtained, or this sort of alkyl boranes are obtained. Alkyl boranes. Now, alkyl boranes themselves are important synthetic reagents in organic chemistry, but when we do hydrolysis of these alkyl boranes, so then we are going to obtain the corresponding alcohol. So what we have seen here is that unlike Markovnikov addition reactions, here the OH group essentially gets attached to the less substituted carbon atom in the olefin. That is why this hydroboration reaction is regioselective in nature, and it undergoes in an anti-Markovnikov fashion. So, because of this discovery, A.C. Brown was awarded the Nobel Prize in Chemistry in the year 1979, because again, the alkyl boranes themselves are very important reagents in organic chemistry. Now, another very important type of reagent that is used in organic synthesis can be prepared starting from this diborane. That is, when we treat diborane with alkali metals like sodium, or even with their amalgams, then we end up with the borohydrides. That is, we will end up with NaBH4 plus, we also obtain NaB3H8. So we start with 2 moles of B2H6 here, and when we treat it with sodium, we obtain sodium borohydride as well as NaB3H8, which is B3H8 anion essentially. So there are other methods of preparation of sodium borohydride, or say alkali metal borohydrides. That is, one starts with the metal hydrides, alkali metal hydrides. So here M is like lithium or sodium, this sort of metals, alkali metals. And then when we react with B2H6, we obtain the sodium borohydride or alkali metal borohydride in quantitative yield here, and BH4 is obtained in quantitative yield. So these are better methods of preparation of these alkali metal borohydrides. But we have already learned in organic chemistry that these metal borohydrides are important synthetic reagents in organic chemistry because they are good reducing agents. Now, when we change the alkali metal in these metal borohydrides, say in the LiBH4 is a very strong reducing agent. In fact, it can reduce esters to alcohol. But when we use sodium borohydride, it's a relatively weaker reducing agent than lithium borohydride. And this is important from the fact or from the point of view of chemoselectivity because sodium borohydride can reduce a carbonyl functionality like ketones, acyl chlorides, as well as aldehydes, while it is not going to attack other functionalities present in the substrate, and that is why we can chemoselectively reduce these functionalities by using sodium borohydride, while the same is not true for lithium borohydride because it is going to interfere with other functional groups which are present in the substrate, and that is why this chemoselective nature of sodium borohydride, reduction by using sodium borohydride, is quite useful in organic synthesis. One example where we see such chemoselectivity is when we take this sort of substrate which contains several functionalities like nitro functionality is there. Here this thiophene is also there. Then the olefin functionality is there, as well as the bromo substituent is also present in this particular aldehyde. And then when we do reduction by using sodium borohydride, then it is only going to reduce the aldehyde functionality over here, and the other functional groups are going to remain intact during this reaction. Sorry, no hydrogen atom attached to this particular carbon atom over here. So this is also true for the substrate here. So what we have seen is that when we use sodium borohydride, the nitro substituent does not get attacked, neither does this thiophene over here, and this olefin functionality also survives this reaction, as well as the bromo substituent over here also does not get replaced, and only the aldehyde functionality gets reduced during this reaction, and that is why it's a chemoselective reduction of the aldehyde group, and it can be achieved by using this sodium borohydride as the reagent. While if we use lithium borohydride, because it is a stronger reducing agent, it is going to interfere with several of these functional groups during this, if we do with this particular substrate. Now there is another very important application of sodium borohydride in industry, and that is known as the Borer process. Which essentially involves bleaching of wood pulp during preparation of or during manufacturing of paper. So during this Borer process, sodium borohydride is used in an alkaline medium to reduce SO2 into dithionate, that is Na2S2O4, that is sodium dithionate, is formed here, while this is going to form NaBO2, and when we try to, this is 8, this is 8, and this is 4. When we try to balance the reaction, we'll have to put these numbers over here. And during the Boral process, essentially this SO2 is reduced to S2O4 negative ion, and this is important process in the bleaching of wood pulp during the manufacturing of paper, and that is why this reaction is industrially important reaction. So we have seen several of the application as well as reactivity of this diborane as well as borohydrides, and one important reaction that we should know about reaction of these higher boranes is that many of these nidoboranes as well as arachidoniboranes, they have Bronsted acidic property because they have bridge BHB linkages in this nidoborane as well as in arachidoniborane. These hydrogen atoms are weakly bonded, and they can be released, or they can get released as H plus ions, and that is why these nidoboranes and arachidoniboranes behave as Bronsted acids. So nido and arachidoniboranes, so Bronsted acidic property. Now what we will see here is that arachidoniboranes are more strongly acidic. Then corresponding nidoboranes, because in arachidoniboranes we know there are more number of bridge hydrogen atoms, and that is why their Bronsted acidity is much more as compared to the nidoboranes. And the second point is that as we for the higher boranes are more strongly Bronsted acidic as compared to their lower congeners, that is, or what we can write is that Bronsted acidity of higher boranes within a series, either in nidoboranes or in case of arachidoniboranes, are higher. So if we compare among the nidoboranes, say before H8 or B5H9, that's right, B5H9, B5H9, B6H10. So for B6H10, the number of bridge hydrogen atom are definitely higher than the number of bridge hydrogen atom is B5H9, and that is why in this case the B6H10 is going to have higher Bronsted acidity as compared to B5H9, and similarly we see that B10H14 is going to have much higher Bronsted acidity than any of these two boranes, and similarly we can go on comparing the Bronsted acidity of nidoboranes. Similarly, in case of arachidoniboranes, we can write before H10, the Bronsted acidity is going to increase as we increase the number of boron centers, because B5H11 will have more number of bridge hydrogen atoms, and B10H16 or B12H18. All of these boranes are going to have higher Bronsted acidity. As we increase the number of boron atoms, the number of bridge hydrogen atoms also increase, and the Bronsted acidity increases in this way. So this essentially brings us to the end of this lecture. What we have learned during this lecture, or what we have discussed during this lecture, is the reactivity of boranes, and mostly we concentrated on the reactivity of the diborane molecule, because that is one of the most studied as well as the most useful or synthetic reagent that has been explored so far for the boranes. And we have seen how one can prepare the diborane molecule in the laboratory, that is by reaction of sodium borohydrate either with iodine, that is diiodine, or with anhydrous acids like phosphoric acid, or with H2SO4. Then we have seen how one can prepare the higher boranes by the pyrolysis of diborane, and we have looked at the mechanism of pyrolysis reaction of diborane, and we have seen how one can optimize, or how one has to optimize the reaction conditions like reaction temperature, pressure, as well as the reaction duration to obtain higher boranes in good yield. Then we looked at how one can trap the transient BH3 unit by making 1:1 Lewis acid base adducts, and we have seen that when we use bulkier Lewis bases like trimethyl amine, say, when we use, then we trigger the homolytic cleavage of diborane to obtain 1:1 Lewis base adduct with BH3. Then we have also seen that when we use less bulkier Lewis bases like ammonia or methylamine or dimethylamine, say for example, in those cases we trigger the heterolytic cleavage of diborane, and then we end up with different types of Lewis base adducts, not 1:1, one is 2:1, and in another case what we have is a hydride acts as the Lewis base, so that we end up with BH4 negative ion. And thereafter we also looked at the hydroboration reaction of diborane, where diborane undergoes 1:2 addition, that is syn 1:2 addition to olefins, and this reaction is essentially proceeds in anti-Markovnikov fashion regioselectively to give us alcohols or terminal alcohols, where the OH functionality essentially gets attached to the less substituted carbon atom of the olefin. And thereafter we have also seen one very important application of these diboranes, that is one can prepare the borohydrates starting from the diboranes, and these borohydrates themselves are again very important organic reagents, as they are good reducing agent, where we have seen difference in the reducing capability of lithium borohydrate as well as sodium borohydrate. While lithium borohydrate is a strong reducing agent, sodium borohydrate is a comparatively weaker reducing agent, and that is why it can be used as a chemoselective reducing agent, as it only reduces either ketones, aldehydes, or acyl chlorides, while it does not attack other functionalities present in the substrate. Then thereafter we have looked at the Bronsted acidity of these boranes, and we have seen why the Bronsted acidity of the boranes, that is the arachnoboranes, are higher than the nidoboranes, while the clozoboranes themselves are not Bronsted acidic in nature, as they do not have any bridge hydrogen atoms. Then we have also seen that on increasing for higher boranes, the Bronsted acidity increases as the number of bridge hydrogen atom increases within a given series of boranes, or either in nidoborane or in arachnoborane. As we increase the number of boron centers, we also increase the number of bridge hydrogen atoms, and therefore the Bronsted acidity is also going to increase. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.